This is chapter 10 from the Electrician program. This chapter is about the service entrance. Very important chapter. The objectives are to list the components of the service entrance, list the service drop clearances specified in the NEC, list 8 basic guidelines when locating a residential service entrance, calculates the size of the service entrance needed based on the power needs of the dwelling, select the power conductors and components for the service entrance, size and install conductors between the meter socket, main disconnect, and the service panel, provide proper grounding for a service entrance, and explain the purpose of the step-down transformer and indicate where it is used. Some of the technical terms that you should look for when going through this chapter is drip loop, insulator, meter enclosure, meter socket, service drop mast, service entrance, service head, service lateral, temporary wiring, and transformer rule. To begin, the service entrance includes all the wires, devices, and fittings that carry electricity from the power company's transformer to the consumer. All electrical energy supplied to the power consuming devices in the building must first pass through the service entrance equipment. The service components protect, meter, and distribute the power to the branch circuits. The service entrance components. The service entrance consists of the following electrical equipment and parts: wires from the utility pole or transformer to the dwelling service point, the service entrance conductors, the meter socket pan or the meter socket, the pan or the enclosure, the service entrance panel with breakers or fuses and a main disconnecting means, grounding system, and the fittings, fasteners, and other hardware necessary to install the service equipment. A quick professional tip: when a piece of equipment is set to be ahead of the meter, the equipment is on the transformer side of the meter. Electricians often use this term when describing where to locate disconnects, OCPDs, which are overcurrent protection devices, and service equipment. The service location. Conductors brought to the building are run overhead or underground. Those coming in overhead from a utility pole are called service drop. See figure 10-1. Those routed underground from either a pole or a transformer pad are called the service lateral. So if you're coming overhead from a utility pole, it is called a service drop. If it's coming underground from a transformer pad, it is called the service lateral. And we're talking about the conductors for the most part, or the raceway, which is the combination of conductors and conduit, or feeders, which is also the combination of conductors and conduit, feeders. You can see in the picture the service lateral, which could only include either a cable or a combination of a cable and conduit, whether it's flexible conduit or rigid conduit, or of various materials including metal and PVC, which is a type of plastic. See figure 10-2. In either type, these wires will be connected to the service entrance wires at the building. Most often, the power company will locate the point of attachment of the service entrance for the electrician. In many localities, this is required. Check the service specifications of the power supplier to be sure of any additional requirements before installing the service entrance. See figure 10-3. Where to locate service? When selecting the service entrance location, use the following guidelines. The underground service entrance conductors, whether enclosed in cable or conduit, should be installed in a straight path to make finding the buried conductors easier. Second, the service conductors should be kept as short as practical to minimize voltage drop. Third, the service conductors must enter the building as close as possible to the service panel. And the service disconnect must be at or very near the point of entry. The service panel should be located in a central and accessible area near the major electrical equipment of the building. The service equipment must be protected from physical damage, water, and dust. And the service equipment cannot be placed in bathrooms, storerooms, closets, or damp cellars. Number of services. A structure can only have one service. Thus, each building will have one service drop or one service lateral. While this is the basic rule, there are some practical exceptions. The following exceptions are allowed. One, a completely separate service is permitted to supply a fire pump or other emergency electrical apparatus, such as lights or standby power. For this, see figure 10-4. If a single service cannot supply a large load demand, another may be added. If structures are so large that no single service would allow electrical access to all the tenants of the building, additional services may be provided. An example of that may be an apartment building. Fourth, a generator driven by an engine or wind may provide additional service. And fifth, the electric power may be supplied by a solar photovoltaic source in addition to the service provided by the utility. Sixth, if different voltages and phases may be required within the same structure, additional services are allowed. The number of services entrance conductor sets. Since the basic rule is that each building will have only one service drop or service lateral, the usual service installation will only have one set of service entrance conductors. Necessary exceptions include multiple occupancies, such as two-family homes, apartment buildings, and commercial establishments with several offices or stores. These occupancies may have any number of service entrance sets tapped from a single service supply. See figure 10-5. The NEC permits a maximum of 6 disconnects from any single service drop or service lateral. See figure 10-6, which illustrates a possible installation of this nature. Regardless of the number of service drops or laterals or sets of service entrance conductors, the service should be carefully planned so that the service entrance conductors are not routed through the building interior unless encased in concrete. The service entrance conductors should also terminate at the disconnect outside or close to where they enter the structure. For this, see figure 10-7. Again, the service entrance conductors should also terminate at a disconnect outside or close to where they enter the structure. Service load. For new single-family dwellings, the NEC requires at least a 100 ampere service. For homes with electrical heating systems or where furniture expansion is likely, 150 or 200 amp service is preferred. However, to be sure that the service is sized correctly for a residence, the total load should be calculated based on the various circuits in the dwelling or of the dwelling. A simple series of calculations can help define this total load. For this, see figure 10-8. Detailed information on these calculations will be presented in Chapter 12, Branch Circuit Feeder and Service Design. Service entrance conductors. The service entrance conductors may be type RHH, THW, THWW, or XHHW, or RHW. They can be run through conduit or enclosed in a cable assembly called the service entrance cable. See figure 10-9. Many service drop installations are made with triplex cable. Figure 10-10. When in conduits, all the conductors are insulated. Again, when in conduit, all in conductors are insulated. The neutral is white, yellow, or gray. The hot wires are black or red. Service entrance cable is similar, but the neutral is bare. Whether conduits or cable is used will depend upon the customer preference, local codes, building structure, environment, utility specifications, and the electrician's experience. In either case, the conduit or cable must be securely fastened to the building with the proper clamps or supports as shown later in this chapter. Sizing service entrance conductors. In addition to proper types of service conductors, the right conductor size is essential. As mentioned earlier, Table 310.15b16 of the NEC establishes the allowable ampacities of insulated conductors. Section 310.15b-b7 instructs us on the proper types and sizes of conductors of 3-wire single-phase dwelling entrances services. Single-phase dwelling entrance services. For this, see figure 10-11. Service drop, mast, and insulator. Very rarely are the service drop, mast, or riser and insulators supplied and installed by the power company. In most situations, the electrician makes the installation. The service drop mast is usually a length of rigid metal conduit or, if allowed, rigid non-metallic conduit. Conduit contains the service entrance cable and is mounted between the service head and the meter. An insulator is a non-conductive device that supports the service drop wires near the service head. It can be clamped to the conduit or attached to the exterior of the building. Insulators are placed approximately 12 inches below the service head. See figure 10-12. The service head. The service head is a fitting installed at the top of the conduit or service entrance cable to prevent water from entering the meter socket and shorting out the conductors. Service heads are designed to be used with either conduit or cable. See figure 10-13. The service conductors should extend through the head for approximately 3 feet to provide a suitable drip loop. A drip loop is merely a formed curvature of the service conductor to prevent water from entering the service head around the cable or conduit. See figure 10-14. Metering equipment. The amount of electrical power used within a residence must be measured so the utility knows how much to charge the customer. The meter is the device that measures and records the amount of electricity used. The meter socket is the receptacle that the meter plugs into. This allows the utility to remove the meter without having to detach any cables. The meter sockets is contained inside of the meter enclosure, which is the box that attaches to the service conduit. The meter sockets and enclosure are usually sold together and are referred to as a meter socket. See figure 10-15. The service conductors enter the enclosure and are secured to the line side lugs of the socket. Note that the neutral conductor is always connected to the center contact and continues essentially uninterrupted through the meter socket on its journey to the service main disconnect or panel. The meter itself will be installed by the utility when the service drop or lateral is completed. Weatherproof connectors. Fittings called weatherproof connectors are used to connect service entrance cable to the meter enclosure when the conduit is not used, or when conduit is not used. One is shown in figure 10-16. The purpose of this fitting is to prevent moisture from entering the meter enclosure. Temporary wiring. Temporary wiring is done to provide electrical power only during construction, remodeling, demolition, repair, or large-scale maintenance of a building. This wiring must be removed when the work is completed. Article 590 of the NEC covers this subject. Although temporary wiring safety requirements may be less exacting than permanent wiring, most of the same rules apply. However, there are several important differences. Temporary wiring can be used on a construction site during the entire term of the construction, regardless of the type of construction. Figure 10-17. In addition, temporary wiring can be brought in for emergency situations, testing, and experimentation. The key factors for installation of all temporary wirings are: all temporary wiring devices and equipment should be located in a safe place and should be as neat as possible. Temporary wiring should be kept overhead as much as possible. All 15, 20, or 30 amp receptacles require GFCI protection. That's ground fault circuit interrupting protection. Protect temporary wiring from physical damage. Use portable ground fault circuit interrupter boxes. For this, see figure 10-18. Grounding must be in compliance with Article 250 of the NEC. All lamps should have protected covers or caging. They should be mounted at heights 7 feet or higher. All circuits must originate from approved panels or power outlets and must have overcurrent protection. All receptacle circuits and lighting circuits must be separated. Weatherproof devices and housings should be used wherever there is dampness or exposure to weather. Locking type plugs and connectors should be used on power ends. And temporary wiring should be inspected frequently for damage. Service disconnects. Section 230.71a of the NEC requires that disconnect means or service entrance conductors cannot exceed 6 switches. Either in a single enclosure or a group of separate enclosures. Again, section 230.71a of the NEC requires that disconnect means or service entrance conductors cannot exceed 6 switches, either in a single enclosure or a group of separate enclosures. Several permissible arrangements are shown in figure 10-19. The main disconnect and service panel. There must be equipment that will disconnect all wiring from the power source. This can be arranged by using a single main disconnect switch or a main circuit breaker that is part of the service panel. See figure 10-20. Regardless of the method used, the disconnect must be located in an accessible place. Further, it must be located as close as possible to the point where the service conductors enter the structure. Service grounding. Grounding the service entrance is vital to the safety of the entire electrical system. Careful attention should be given to this section to ensure a thorough understanding of the procedures involved. In addition, you should study all sections of Article 250 of the NEC before undertaking any electrical installation. Grounding the service entrance involves connecting the neutral or white service conductor with earth. Again, grounding the service entrance involves connecting the neutral or white service conductor with earth. This is done by means of the grounding conductor. This conductor connects the neutral lug of the meter housing or the neutral bus bar of the service switch or the service panel to the metallic water pipe system or to the metallic water supply pipe. For this, see figure 10-21 on your screen now. In addition to or in place of the water supply pipe, other grounding electrode systems shall be used, like metal frames of buildings, metal electrodes encased in 2 inches of concrete within or near the bottom of a concrete foundation, or a 20-foot of 2 AWG bare copper wire buried not less than 2.5 feet below the surface. Underground metal tanks or other such underground systems or structures. A rod or pipe electrodes that are at least 8 foot long, fully driven into the ground or buried no less than 4 feet below the surface. Metal plates of no less than 2 foot square surface in area where 2 or more grounding electrodes are used. They should be separated by a distance of 6 feet and bonded or linked with a copper conductor. The resistance between the grounding electrode and the earth must not exceed 25 ohms. Again, the resistance between the grounding electrode and the earth must not exceed 25 ohms. Grounding electrode conductor. The grounding electrode conductor connects the grounding bus bar to the grounding electrode. This conductor should provide little resistance. For that reason, the conductor is typically copper, aluminum, or copper-clad aluminum. The grounding electrode conductor must also be firmly attached to the grounding electrode using approved fittings. Figure 10-22, as with all conductors involved in grounding, the grounding electrode conductor must never be interrupted. Sizing the grounding electrode conductor. Table 250.66 of the NEC indicates the proper sizes for the grounding electrode conductor. This is based on the service entrance conductor size. See figure 10-23. That's at the bottom of your screen. For example, if the installation of a 200 amp service entrance using 3/0 AWG copper service wires would require a 4 AWG copper grounding electrode conductor. Service clearances. Where overhead services are installed, certain regulations concerning clearances must be strictly observed. The NEC indicates that clearances for overhead service drop conductors shall be as follows. Above roofs, figure 10-24, top of your screen. A, 8 foot as measured vertically from all points. B, 3 foot if the slope is not less than 4 inches to 12 inches. C, 18 inches over an overhanging portion of a roof. Figure 25, 10-25, at the bottom of the screen. Above final grade. A, 10 foot above sidewalks. B, 12 foot above residential driveways. C, 18 foot above public alleys or thoroughfares subject to truck traffic. At building openings, figure 10-26, A, not less than 10 feet above all finished surface platform or other accessible surface. B, no less than 3 feet from a window in any direction except above the window. Additional information regarding clearances is found in section 230.24 of the NEC. Service completion. When the service entrance installation or rough-in is completed, it is inspected by the electrical inspector. After this, the power company will install the service drop or lateral by connecting the wires from the transformer to the service entrance conductors. Figure 10-27 shows a typical completed service entrance. Note the drip loops discussed earlier, as well as the positioning of other components in the finished system service or in the finished service system. Transformers. While the residential electrician will not be working on transformers, it is helpful to understand how transformers are made and how they work. Due to the voltages involved, you should be careful when working around this equipment. Transformers are installed and serviced by trained line workers employed by the power company. Transformer operation. A transformer has a relatively simple structure. Figure 10-28. Basically, it contains 2 coils of wire or windings and a common metal core. When an alternating current is sent through the first coil, the primary, it magnetizes the metal core. For this, see figure 10-29. This magnetization of the metal core causes surges of magnetic flux. The surges are constantly reversing direction. This magnetic flux also moves through the coil, which is called the secondary. The current is created, or a current is created there too. Since the same magnetic flux exists through or throughout the core, the same voltage per wire is created. Therefore, any voltage difference is the direct result of the differences in the number of turns in the primary and the secondary windings. The transformer rule, mathematically stated, the total voltage in the primary coil is to the total voltage in the secondary coil as the number of turns in the primary is to the number of turns in the secondary. Again, the total voltage in the primary coil is to the total voltage in the secondary coil as the number of turns in the primary is to the number of turns in the secondary. This is the transformer rule, and it can be expressed as an equation as voltage of the primary divided by the voltage of the secondary equals to the number of turns of the primary divided by the number of turns of the secondary. Power into and out of a transformer is ideally the same. Since voltage changes within the transformer, so must amperage. Remember, power equals volts times amperes. For this reason, the amperage must change proportionately, but inversely, as does the voltage. This can be stated mathematically as an equation. Primary voltage divided by the secondary amperage is equal to the secondary voltage divided by the primary amperage. For example, suppose a primary voltage entering a transformer is 12 volts. The example is on the screen. And the primary amperage is 20 amperes. What will be the secondary amperage if the secondary voltage is 120 volts? Using the equation just given, 12 volts divided by an unknown quantity, we have that as X in this case. 20 volts is equal to 120 volts divided by 20 amps. Top of your screen. By cross multiplying, 12 volts divided by X equals to 120 volts divided by 20 amps. We get 120 X, or 120 multiplied by X on one side, left side, equals to 240. Further simplifying, we divide 120 by both sides, which we get X equals to 240 divided by 120, which we get X equals to 2 amperes as an answer. Since the transformer changes voltage, it can either increase or decrease the primary voltage. That is the secondary voltage. I think there's a typo here in the text. Again, since a transformer changes voltage, it can either increase or decrease the secondary voltage. One that increases the primary voltage. Let me take that back, excuse me. Since a transformer changes voltage, it can either increase or decrease the primary voltage. And that is on the secondary side. That's where you get the increase or decrease. A transformer that increases the primary voltage is called a step-up transformer. A transformer that decreases the primary voltage is called a step-down transformer. For this, see figure 10-30. Directions for selecting the proper transformer to match the electrical load are found at the end of the chapter.